This is Richard Walker from Lucidate. In this video, we'll look at the concepts and intuition that underpin popular AI methods. We will examine neural networks, a popular AI technique for classification problems. This includes computer vision, where we identify and classify objects based on pixel intensity. In this video, we'll look at how modern AI techniques differ from conventional computer programming. We'll look at artificial neurons. When stacked together and connected in layers, these form networks called artificial neural networks, or neural networks for short. We'll see how these simple, tiny units can solve very complex problems. The clever bit of mathematics here is to use calculus rather than logic. As we'll see, these simple neurons all have parameters that can be tweaked. In a big enough network, the number of parameters becomes sufficiently large for us to be able to solve challenging tasks. We'll see how we can use calculus to nudge, tweak, and adjust this vast number of parameters. The result of these nudges, tweaks, and adjustments will be a set of optimal parameters for solving a particular problem. So after looking at the definition of artificial neurons, we'll turn our attention to calculus, in particular rates of change. These rates of change, or derivatives, tell us how much one number changes when another number changes. As we'll be looking at multivariable calculus, we'll see how several numbers change in response to the changes in a bunch of other numbers. So, how does AI differ from conventional techniques? Well, a complete list of differences would be lengthy. Here, I'll major on a very simple difference. In conventional programming, you might ask a subject matter expert what rules or business logic exist to define a process. You'd also ask them what attributes define the objects and pieces of data that you're processing. Things like height, age, body mass index for a medical system, currency, quantity, price for a finance system, stuff like that. Then you'd write a set of functions that operates on inputs that gives you the desired output. AI turns this process inside out. In a technique called supervised learning, we'll show a classifier a bunch of input data. For a meteorological system, this could be pressure, wind speed, and temperature. For a speech recognition system, it would be the electrical signals from a microphone. For a vision system, the intensity of pixels. Then we show it the corresponding outputs, weather patterns, words, and image labels that correspond to those particular inputs. We then get the computer to come up with the rules that link the patterns in the inputs to the correct output. We don't ask a subject matter expert the rules that make this a picture of a cat or a dog. Instead, we get the computer to identify the patterns in the pixels that classify this image. So in our system, our objects are neurons. We'll describe their data attributes and operation shortly. And our methods are tweaks and nudges to the neuron's parameters to minimize a cost function. After our explanation of neurons, we'll look at how calculus helps us achieve this. This is an artificial neuron, so called because it mimics how we understand biological neurons to work inside our brains. As the name implies, a neural network is a bunch of these units networked together somehow. And the neuron is simple. Seen from the outside, it's just a number, often referred to as an activation. For some purposes, we'll want neurons to have any value they might wish, or we can limit the values to a specific range, perhaps from 0 to 1, which might be useful for probabilities, or perhaps from 0 to positive infinity. The choice will usually be a free one and will depend upon the problem we're solving. Seen from the inside, a neuron is just a simple function. It takes inputs. These inputs get multiplied by weights, and the resulting sum has a bias applied to it. This is then fed to a function that gives the neuron its activation. The bias itself is also inspired by biological neurons. It determines a threshold above which the neuron will fire or become activated. There are a choice of activation functions available, and they all have their own role to play. We'll look at several in this series. Here's one called a sigmoid function. It has some nice properties. It's continuous. You can calculate its derivative anywhere. And as you can see, it keeps the output values between 0 and +1. For some purposes, we will want that. If we had a bias term, we can see how the sigmoid behaves for positive and negative biases. You can see here how these biases act as a threshold. This will turn on the neuron at either higher or lower values of our total weighted input, x. For a long time, the sigmoid function was the most popular activation function, still very widely used. But for now, the most useful, most common, and frankly, the most easy to understand is the ReLU, rectified linear unit. This outputs an activation of 0 if the weighted sum is below the bias. Otherwise, the activation is just input and bias. The inputs come from some observation, in the case of vision, the pixel values of a camera, or from other neurons. This is the network bit of neural networks. These neurons stack into layers, with the outputs of one layer serving as the inputs to the next. As we add neurons to layers and add more layers to our network, we increase the number of weights and biases. These weights and biases serve as parameters that are nudged and tweaked. How should we nudge and tweak them to achieve our desired result? When I pose this question to some of my colleagues in capital markets, a large number of them say Monte Carlo simulation. Monte Carlo entails randomizing all the weights and biases, then running the test samples through the network and saving the set of parameters that gives the best result. Given enough compute and a lot of time, you'd need a huge amount of both, this might be expected to yield a decent result. It is a solution, but there are better solutions. This is where calculus and derivatives come in. The sensitivity of a single number to a change in one other number is pretty straightforward. We can usually draw a nice chart to help show these relationships. As soon as we start adding other variables, things can get messy. We usually have to add subscripts, a bunch of i's, j's, and k's. Doing all the index chasing gets hard, and a lot of us find it difficult to conceptualize and give up. But actually, the maths doesn't get any different or more complex when you get more dimensions. For a computer, these subscripts and dimensions just mean more loops, or more rows and columns in a matrix, or more axes in a tensor. Sure, more dimensions of data might mean more compute time or a need to get more hardware, but the mathematics and concepts remain as they are. To gain the necessary intuition, let's look at a practical example: driving a car. You have an accelerator, a brake, a steering wheel, and a gear stick to act as controls. There's a sensitivity to the car's motion to how much you press the accelerator or turn the steering wheel. You also know that this isn't a simple static sensitivity. Instead, it depends upon a whole bunch of other variables. If you push the accelerator only slightly when you're going fast downhill, you'll get a big change of speed. Conversely, if you're going slowly up a steep hill, you can floor the accelerator and nothing much will happen. When moving very, very slowly, you can yank the steering wheel all the way around and gracefully turn around a corner. But at high speeds, with the tyres on the limit of grip, even small movements of the steering wheel might be catastrophic. You could end up skidding or rolling the car. I hope that this driving analogy helps in understanding derivatives and calculus. The aim here is to show practical, familiar examples where we have rates of change between inputs and outputs. The key takeaway is to show examples where these relationships are neither linear nor static. This is certainly true in driving. There isn't a fixed change in speed in response to a 5-degree change in accelerator position. The derivatives of vehicle motion will depend on many other factors. The same is also true of braking, steering, and gear shifting. Exactly the same holds true for the rates of change between inputs and outputs in our neurons, both artificial and biological. So to summarize, in conventional programming, we write some rules to transform input data into results. In AI, we take inputs along with corresponding results and get the computer to produce a mapping between the two. If we're successful, this mapping will be able to generalize, meaning it will give correct responses to information it has not already seen. A neuron is a simple unit modeled on a biological neuron. A series of inputs will generate its activation. If you connect enough neurons together, you can solve problems that you can't solve with conventional logic or if, then, else statements. We can use calculus to help us determine the correct weights and biases. More on this in the next couple of videos. There's a strong analogy between nonlinear, multivariable derivatives used in neural networks and driving a car. When the maths notation becomes dense and off-putting, it's often helpful to invoke an analogy. We can use our intuition to help us better conceptualize the mathematics, rather than trying to figure out what all the subscripts, indices, and variables in complex formulae mean. This is Richard Walker from Lucidate. Join me in the next video as we discuss the use of a cost function to incentivize the network to come up with optimal weights and biases, and introduce a computer vision task and begin to train a simple neural network to recognize thumbnail images of clothes.